Hello, and everyone, and welcome back to stage one at the conference that we've got going today. So just to remind you of myself, I'm Jake Rigby. I'm Head of Innovation and Research at BMT Engineering Consultancy. Very apt helping to chair this conference because a lot of the topics are innovation focused, purely driving our sector forwards. So on that note, it gives me great pleasure to announce our next speaker, who is Jeremy Nahon from leads simulation and software engineer for offshore wind at Akselos. He's here today to talk about the path to optimize design, integrated load, and structural analysis for floating wind. Great topic. So over to you, Jeremy.
Thank you, Jake. Thanks for the introduction. So that's great. Thanks for attending, everybody. I'm Jeremy Nahon, lead simulation software engineer at Akselos for offshore wind. And so at Akselos, we've made it a mission to unlock detailed design optimization for floating wind, incorporating structural performance. And what I'm going to be presenting to you today is a crucial step towards that goal, specifically integrated load and structural analysis for floating wind. So before I dive into what that is specifically, I want to give a bit of context and explain what the issues are that are preventing the implementation and usage of detailed design optimization for floating wind assets. So as you probably know, these floating wind foundations and turbines are complex. They go under different kinds of physics and, hydrodynamics for the foundation, aerodynamics for the turbine, you've got structural mechanics throughout. And so for each of these components in physics, we have dedicated solvers that can be expensive to run, as slow as well as quite expensive to learn and to ramp up experience in. So what typically happens is we have these dedicated teams or people within companies and within projects that work on one single aspect, one single component. And so we have these siloed workflows, which make it very difficult to have holistic designs. You can imagine what needs to happen to get the change at the foundation level to be passed onto the turbine performance. You have to take the output from the hydrodynamics and map that onto the turbine and so on and so on. So this makes it very difficult. If we take a step back, what that means is that there's no proper exploration of design space early on in project development, which means that costs usually are higher than they need to be. And there's also a risk that, is kept within the product development for a long time. And this probably contributes to why the takeoff of floating offshore wind is not as fast as we expected it to be. So the work I'm presenting today inscribes itself in a wider project called FOWPTIM. And so this is a research project led by Akselos, ourselves, and Muse Labs, our partners. And this addresses specifically these issues with design optimization within floating wind development. And so we want to provide a solution that has three goals: accelerate the workflow in analysis and design. And here by accelerating, we mean as well cleansing the designs. That means removing inefficiencies that make this a boring and difficult workflow for engineers. We want a solution that can be applied to all floater types. And then in terms of outcomes, we want our solution to provide real CapEx reductions by reducing the mass of these floating offshore foundations. And we aim to do this by implementing and using design or automated design optimization in a smart way. And how are we going to make this possible? We have two enablers. The first one is this block here. That's the seamless design toolchain for integrated load and structural analysis. That's precisely what I'm going to present today. And that's the integration of Capytaine, the potential flow solver, OpenFast, the global analysis solver, and Akselos RB-FEA for structural analysis into a single environment that provides cloud performance computing. And so this is exactly what I'm going to present today. And so I'll give you plenty of details about this. And this is at the core of the FOWPTIM project. This is what enables the design optimization. And so design optimization is the second enabler, so this block here. And this is still work in progress. And I won't go into too much detail here, but the idea is that we have a two-level multi-fidelity framework. The first level is focusing on the global shape of the floating foundation and trying to address how these changes affect the hydrodynamic performance or the global performance. And then the second level really focuses on the internal structure of the floating foundation and really tries to bring down the extra mass without downgrading the structural performance or the global performance of these turbines. And so this consortium, FOWPTIM, is made up of Akselos and Muse Labs. So Akselos, to give you a brief summary, has developed the RB-FEA solution engine, which is a much faster, much more efficient way of running FEA simulations. So it's based on the reduced basis approach, but we've added some specifics and little bits of icing on the cake that makes it much faster and much easier to use. So one of these is component-based modeling, which makes it much faster to generate the reduced basis. So if you're doing a reduced basis workflow, you start with an offline phase, which consists in generating the reduced basis based on a database of information that you have. But this is still difficult to generate if you're looking at the entire model. So we've broken up these models into repeatable components that are much faster to solve and then can just be duplicated to generate the full model. We also have a parametric approach, both in terms of loads, but also in terms of design parameters. So we can directly embed for example, the thickness of shells into our reduced basis. And this is key for the design optimization. And this actually has been presented by my colleague, Dr. Romain Pinguet at WESC earlier this year. And I'm happy to provide the link to this presentation if necessary. And on top of that, we have error indicators that ensure that our solutions are FEA compliant. So industry FEA compliant all the time. And so what that means is that we have a workflow that enables us to be scalable, hyper accurate, and hyper fast. So typically we can solve an FEA simulation 1,000 times faster than conventional tools such as ANSYS or Abacus. And we're collaborating with Muse Labs. And Muse Labs is a company that's specialized in simulation engines for a range of physics. And they are the ones who are developing the Capytaine code, in particular Dr. Mathieu Ancelin. And this started as a Python rewrite of the NEMO code, specifically targeted at wave energy converters, and it's been supported by NREL and Sandia National Labs. And so the goal of Capytaine is to be open source, Python compatible, so it can be easily embedded into engineering workflows and highly scalable. And so with these two ingredients, Akselos' experience in FEA simulations for offshore structures and Muse Labs' experience in simulations in general, and in particular with Capytaine and wave energy converters, we really think we have a good collaboration that can really fulfill these targets of bringing design optimization into reality. So let's dive into the ILSA toolchain. So the core innovation at the heart of ILSA is the seamless integration of Capytaine, the potential flow solver, OpenFast, the global analysis solver or coupled analysis, and Akselos. And what makes this possible, aside from just the software side of things, is another innovation that was developed at Akselos, which is the load mapping methodology. And this makes it possible to accurately, robustly take all the loads from the coupled analysis and map these onto our FEA model. So that includes inertial loads, acceleration, force loads, tower-based force, mooring line forces, as well as hydrostatics, radiation, diffraction, and Morrison loads. And what makes this easy, especially easy with Akselos, is that we have the capacity to build holistic models of these foundations. So it's often the case that people tend to submodel when they're doing FEA analysis parts of these foundations, and of course that creates problems when it comes to mapping the loads from the rigid body simulation, so the coupled analysis, onto the FEA models. And so we completely remove that issue, and we just take the stuff that's So we have this one-to-one similarity, geometric similarity between the OpenFAST model and the Akselos model. And so the way we do it, briefly, for radiation diffraction in particular, is we take the panel pressure in frequency domain that comes out of Capytaine. So this is what we call the hydrodynamic database here. We map that onto our Akselos FEA model. And then we take the motions from the OpenFAST output and combine these with the frequency domain pressures to get our time domain pressures on the model. Now, computationally, ILSA is based on container-based implementation. So each one of these solvers lives inside its own container, Capytaine, OpenFAST, and Akselos. And this is important because it means the environments are much more manageable. And more importantly, we can easily allocate the necessary resources to each of these solves. And this is key if we want to leverage the cloud computing power that we have at Akselos, or in general, to ensure that we can get answers as efficiently and as robustly as possible. So what goes into the ILSA toolchain? So as you'd expect, we have inputs for each of these solvers. So the Capytaine, the OpenFAST, and the FEA solver. And so we don't make things too complex. We just take existing models. So we use the panel mesh for the Capytaine solver, the FEA mesh and model for the Akselos solve, and the OpenFAST model for the OpenFAST solve. And on top of that, we have an extra set of inputs, actually a single input, which is the definition of the load cases. And so this is an input file that contains all the load cases and all the different parameters of these load cases. And so these OpenFAST and Akselos models are very data rich, but we think that's an asset because what it means is that the user can prepare their Akselos and OpenFAST models. Once these are prepared on sort of test cases, they're ready to run for the full DLC analysis, which is exactly what the ILSA toolchain is designed to do. And so I've taken this screenshot from our web-based platform where we have these 4 boxes of inputs, which each correspond to load case definitions, panel mesh, FEA mesh, and OpenFAST model. And so I'm going to show you, trying to be as quick as possible, and give you a demonstration for the OC4 deep sea wind model. And so we've generated a panel mesh, placed the center of mass correctly, which includes the tower and rotor nacelle assembly mass. And then we use the OpenFAST model, the open source OpenFAST model, which is a 5 megawatt OC4 semi, including the Discount OC3 high wind controller. And then for the FEA model, we made sure that the mass of our FEA model corresponds to the OC4 source material, both in terms of absolute mass and in terms of center of gravity or center of mass. And we see that these match perfectly. And so what happens? So once the user clicks on the ILSA run button, we have an ILSA parent job that is responsible for orchestrating and triggering all the sub-jobs. Of course, the first job that we need to run is the Capytaine potential flow solve. And so this is dependency, or both Akselos RB-FEA and the OpenFAST solve are dependent on the results of the Capytaine solve. So we need this to run first. So this is going to run. As soon as it's over, what happens is that the ILSA parent job automatically triggers the OpenFAST analysis for each of the defined load cases. So in this case here, we have 3 load cases that have been defined by the user. And the ILSA toolchain will automatically parallelize these jobs. It will take the inputs that have been defined for OpenFAST, duplicate these inputs corresponding to each of the definitions that have been given in the load case file, and then run these in parallel. And does this completely automatically. Once those are completed, we move on to the intermediate steps, which consists in taking the outputs from the Capytaine solve and the OpenFAST solve and mapping these onto the Akselos FEA model. So that includes the panel pressures in frequency domain and the motions that we need to actually reconstruct the panel pressures in time domain. And so this is what happens here. We also have 3 jobs because we have a job for each of these load cases. And then finally, the final step, and that's the structural analysis. So the FEA model is ready. We've taken all of the inputs, all the outputs from the previous solves and mapped them onto the FEA model. And now we can actually run the structural analysis. Here, what you see is a deterministic fatigue request. So it's not just a simple FEA solve, it's an FEA solve plus the fatigue post-processing. And so at Akselos, we've pre-built these solves that contain standard compliant fatigue or strength check post-processing codes. And these have been designed to leverage as much as possible the cloud computing power. Once all this is completed, the user can access their outputs, and on the web-based platform, all these jobs are listed as successful. But one thing the user can do before they actually access the outputs, and something they can do actually throughout the entire running of the ILSA job, is go through the verification step, so the load mapping verification step. And that's something that will sit actually between the structural analysis and the open-fast couple analysis. And what it does is it ensures that the forces that are generated by the open-fast solver correspond to the forces mapped onto the Akselos model. And so those are the net forces, the rigid body forces. And so what we see here, what I'm presenting, are the diffraction, radiation, Morrison drag, and hydrostatic comparisons between open-fast and Akselos. And we see that all map really well. And this is information that's continuously generated by the ILSA toolchain, and something that the user can check at any time. So if necessary, if there's something wrong, the user can know before having to run expensive FEA simulations. The user can know whether to turn off or continue the simulation. And what we recommend doing, how we see this workflow actually unfolding, is that there's a first batch of, let's say, test simulations that can be used to precisely analyze this output and make sure that everything works. And once that's the case, the user can just throw in all of the load cases that he needs to run. And so then the user can access the results. So obviously stress outputs can be presented, and we've also developed interfaces that allow the user to interactively view the responses from the analysis. So in this case, we're showing fatigue. So we see the fatigue hotspots. And what's key here is that we give a breakdown of the impacts of each DLC. So this is the graph here on the right, the impacts of each DLC on the asset itself. And all this information can be generated into a PDF report. A key aspect that I want to address here is the computational footprint and the computational usage of the ILSA toolchain, and what it means for users of the ILSA toolchain. So what we know from experience is that a typical open-fast analysis, so say a DLC 1.2, considering a time step of 0.05 seconds, which equates to 72,000 steps for an hour of physical time, and where we turn on Servodyne and we include second-order waves, this amounts to approximately 0.6 CPU hours for 1 hour physical time. On the other hand, if we take the FEA analysis breakdown, in this case for fatigue, where we consider a 1.7 million degrees of freedom model with 725 hotspots, and we consider, so we've done this analysis for 500 load cases approximately, with a 10 Hertz time resolution, then this equates to 3 CPU hours per hour of physical time. And so so I wouldn't say that the open-fast analysis is negligible, but what's key to understand here is that both of these processes are highly parallelizable. So the open-fast case is parallelizable across the load cases, which is something that we've implemented already into the ILSA toolchain. And the same thing for the load cases for the fatigue analysis, as well as for the hotspots analysis, which are also parallelizable. And so what we know is that we've been able to complete 1,000 load cases in approximately 24 hours, just for the fatigue side of things. And so if we extrapolate this value to the open-fast, to include the open-fast analysis, we can estimate that a user can run an entire DLC analysis, say 1,000 load cases, in approximately, conservatively 36 hours. And this is an important metric to keep in mind, because it means that the user could just click a button, run the ILSA toolchain, do something else of much higher value, and then get the full results. within a 36-hour time frame. So that brings me to the conclusions and the perspectives. So what I presented to you today is the fully integrated load and structural analysis. And this is what we've termed as pillar 3 of our pathway to multi-fidelity automated design for floating offshore wind platforms. The first one is tractable and parameterizable analysis with RB-FEA. The second is the global to local load mapping, which I've mentioned. And the fourth one will be the automated design optimization. And so what we're seeing here today is that we've built a method that can eliminate the inefficiencies in the analysis workflow. And so that means that users can quickly get a full response that includes global analysis, that includes structural analysis of the floating offshore structure. But what it means on top of that is that we now have this completely hands-off pipeline, which can directly be embedded into our design optimization tool. And so my hope is that soon I'll be able to talk to you about the design optimization algorithm and present some promising results that showcase our reduction in CapEx and material mass. Thanks, everybody.
Brilliant. Thank you very much. And yeah, great presentation. Really interesting to see the results coming through on that as well. I've got one question to start around the methodology that you've created around this. Is that approved independently or had any kind of wider input to that?
So we have approved parts of it. So if I go back to this graph, for example, so the structural analysis part of it, and I've mentioned that we've got these pre-built solvers that include fatigue and strength check. So these are all standard compliant. All the structural analysis is standard compliant. In terms of the rest of the workflow, we are collaborating, and actually within the FOWPTIM project, we are collaborating with class companies such as ABS, and their task is going to be to actually look at this and validate this entire workflow.
Brilliant, thank you. We've got a couple of questions on the Q&A. Someone has asked for a link to a presentation from your colleague with regards to incorporating shell thickness. Maybe that'd be better to send direct through message or share on the wider chat rather than on the Q&A, but we can discuss that afterwards. And then another question here. Highly grateful for the presentation, but can you share more information on the Akselos FEA model? How is it different from other products in the market? So maybe a bit of a, for the last 2 minutes, a bit of a elevator pitch.
So what's different with Akselos models? So Akselos models at their core, I think the key takeaway for Akselos models compared to conventional models is that we can get FEA simulations in 1,000th of the time of conventional FEA. And so how do we achieve that? It's the slide I'm presenting here. But what it means in terms of the user workflow is actually not much different. There are some specificities like componentization, which are different from what tends to happen with Abacus or ANSYS. But other than that, the workflows are similar. We apply forces, we apply pressures. And once the model is trained, as in once the reduced basis is created, you get solutions in an instant. So yes, perhaps another difference with conventional models is actually the training part. But the training part, once you compare to, I think I have a slide for this. Let me see if I have a slide. Once you compare to the actual time of resolution, especially if you're considering to run a huge number of load cases, is completely negligible. It completely disappears relative to the real computing power, computation time consumed by running, I don't know, 1,000 load cases. And so, yeah, so what you're left with is simulations that take a fraction of the time that conventional FEA simulations would.
Brilliant. Thank you. And yeah, great high pressure elevator pitch there at the end. So thank you. There's been a flurry of some additional questions being posted on there. Unfortunately, we don't have time to go through all of them. So Jeremy, if I could ask you, if you go to the Q&A, you can see the individual and you can directly message them or add to the Q&A or the wider chat function some responses to those comments, that would be greatly appreciated. So yeah, well, thank you very much again, Jeremy, for a great presentation.
Thank you so much. Thank you, Jake. Thanks, everybody.